Hi kids, time for more derivative tests. Now, most of today is going to be a review of what we did in the last video, but there is one new concept, and that's this. Remember that I told you we had the first derivative test for extrema and the second derivative test for concavity. Right? And each one of those had a similar format, right? Extrema, which means you also got increasing and decreasing. Second derivative test for poi, meaning you also got concave up and concave down. Now, each one of those had a very similar format. You get the appropriate derivative. You find out where it does not exist, where it is equal to 0. If you have endpoints, you gather your suspect list. You make a line. You make a lineup, right? You make your number line. You test your intervals around there. That's all swell. But the second derivative test can also be used for extrema. The first derivative test can also be used for concavity, right? So they are interchangeable, but the most important here is using the second derivative test for extrema. Now, I'm going to get up, I'm going to do a little lecture. I remember what it's like to be a student. I do. I understand that I just taught you how to use the first derivative test to extrema, and I'm about to show you an alternate way to find extrema. It is very tempting to put your fingers in your ear and go, no, don't talk to me, don't talk to me. I'm learning the first derivative test for extrema. I don't want to talk about that. I don't want to talk about another way. Stop. Right? I get it. I understand. Please believe me. You are going to want to use the second derivative test for extrema in certain situations. Further, AP is going to force you to use it. So it is in your best interest to learn it now. And then when we get to the series unit, there's going to be a time where you have to use the second derivative. You won't be able to use the second derivative test for extrema. The reason why is because the whole idea of that number line where you have to test values around where your derivative does not exist or is equal to 0. The second derivative test for extrema takes the number line out of the equation. Ha, pun intended. The second derivative test does involve the first derivative, though. If you have a critical point, not an extrema necessarily, just a critical point, which is where the first derivative is equal to 0, does not exist, just equal to 0. And at the same time, the second derivative is negative at a particular value. Then you have a local maximum. If the first derivative is equal to 0, which is a critical point, and at the same time the second derivative is positive, then you have a local minimum. So hopefully you are writing that down, and now I'm going to do a little drawing. For number 1, let me do, instead of all those words, if the first derivative is equal to 0, it means I have a horizontal tangent. It doesn't mean I have a max or a min, right? Think about x cubed. X cubed has a horizontal tangent at 0, but does not have a turning point at 0 because the first derivative doesn't change sign around it. But if your derivative is equal to 0, you have a horizontal tangent. And this is at a particular x value, right? So let's say at a particular point, the first derivative is equal to 0. At the same time, the second derivative is negative. But what does the second derivative being negative mean? concave down. So I have a horizontal tangent, and at the same time I'm concave down, I must be a local max. Number 2. If you have a number, a certain x value, and the derivative at that point is 0, but at the same time, the second derivative is positive, meaning what? You're concave up. If you are concave up at a point and you also have a horizontal tangent, you must have a local min. This is handy, and it means I don't have to test values, right? A bunch of values around. I don't need a number line. It does require that I know where the first derivative is equal to 0, and it does require that I know where the second derivative is positive or negative. Now, there's an issue. This test does fail. The second derivative test for local extrema does fail if the second derivative also equals 0. Sorry, I didn't mean to flip that soon. If f double prime also equals 0, or if f double prime does not exist. When that happens, I just have to go back to my number line work. Okay, but the power in the second derivative test for extrema is that I just have to know where the first derivative is equal to 0 or does not exist, and then I have to know where the second derivative is positive or negative, but only at a point, not in an interval, right? I don't have to worry about an interval. It is only at a point. So let's do this. Find a local extreme value of f prime using the second derivative test. So if the direction said to use the second derivative test and I used the first one, I would get answer points, but I wouldn't get rubric points for the work. So finding the first derivative, where is the first derivative equal to 0? Right, I set it equal to 0 and then divided by 3. So that's my suspect list. Question, do I have endpoints? No, it's a cubic and they didn't chop my domain, so I don't have to worry about suspects. So I only have 2 suspects. Instead of making a number line, go ahead and find the second derivative. Your second derivative is what you need to test. Take your suspects to the second derivative lineup, if you will. You plug in 2 and I get 12. I don't really care about 12. I care that it's positive. I plug in -2, I get -12. I don't really care. I just care that it's negative. So what's true? At x equals 2, f prime is equal to 0, and f double prime is positive. That means I have a horizontal tangent and I'm concave up. Therefore, x equals 2 is a local min. X equals -2. What was true? F prime was equal to 0. F double prime was negative. Therefore, I had a horizontal tangent, but concave down at x equals -2. Therefore, x equals -2 is a local max. Now, this asked me for extreme values, which means they actually want the height. So I need to go back to the original. Values means height. So I have to go to the original and plug in 2. And I have to go back to the original and plug in -2. Is that 8 minus 24 minus 5? And -8 plus 24 minus 5, if I've done my math right there, whatever that is, blah, blah, blah. Who cares? All right. That was the only new topic for today. Second derivative test for extrema. So let's do some review problems. Some review topics, right? The first derivative test for extrema. If I have a continuous function f of x, if f prime changes sign from positive to negative, then I have a local max. If f prime changes from negative to positive, then I have a local min. Notice in both cases, I show that this illustration has where the first derivative is equal to 0 or where the first derivative is undefined. That's just your suspects. The important part is that your derivative changed from positive to negative, or your derivative changed from negative to positive. If the derivative does not change sign, even though the derivative is equal to 0, or the derivative does not exist, you don't have an extreme value, right? Here's those two cases. Look, I have a horizontal tangent right there, but the first derivative is positive and stayed positive. I have, where the first derivative does not exist, I have a little corner or cusp or whatever thing here. But the derivative is negative before and negative after. No extreme point. Here's the endpoint analysis that I did at the end of the last video. If you have extrema, if you have endpoints, if the first derivative is negative after the left endpoint, then you are rising to, you are falling from the maximum, right? If you have a left endpoint and your first derivative is negative, you are falling from the left endpoint. The left endpoint then is a local max. However, if you have a right endpoint, if you still have a right endpoint, and the first derivative is negative, then you are decreasing 2. And the right endpoint is a local min. Conversely, if you are a left endpoint and the first derivative is positive, then you are increasing from the left endpoint, and the left endpoint is a local min. If you have a right endpoint and your first derivative is positive, that means you are increasing to the right endpoint, and your right endpoint is a local max. And that's what this shows. Left endpoint, first derivative negative, which means you are decreasing from the left. Left endpoint, first derivative positive, means you are increasing from the left endpoint. First derivative negative on the right endpoint. First derivative negative, you are decreasing to the right endpoint. First derivative positive, which means you are increasing to the right endpoint. You only, of course, have to do endpoint analysis if you have endpoints. So this is on a handout that we have linked to our Canvas page, and that is also, all that stuff that I just gave you is on the Canvas page, on that packet that is linked. It's also in files. These are nice, this is a nice little synopsis. All these drawings here is what I just went over. This is a nice drawing here. These hints are from AP. AP says your work is the number line or a chart that you make when you are finding extrema. If you are asked to justify, you must use words. You do not have to use full sentences. You don't have to use commas. You don't have to capitalize, but you do have to use words. The first derivative changed from positive to negative, therefore there was a local max. Okay, so I've given you some examples here, an example here. Also, avoid using pronouns. This again is from AP. So if a student says something like it, or writes, it is increasing because it is positive, right? What does it? It means two different things there. That's the only English requirement that you have here. No capitalization, no punctuation necessary, no even correct spelling necessary. Don't overuse your pronouns. Don't say it. Say the original, or f of x, is increasing because f prime of x is positive. Okay? Concavity review. You don't talk about concavity or points of inflection at endpoints, so we're only talking about open intervals. If the second derivative, if you're concave up, the first derivative is increasing. So if you know y prime is increasing, you know you're concave up. That's the first derivative test for concavity. If the first derivative is decreasing, this is new, sorry. If the first derivative is decreasing, that means your original is concave down. If your first derivative changes from increasing to decreasing, or vice versa, then your original has a point of inflection. Right? There's our nice sine function. Tangent lines are increasing. I'm sorry, tangent lines are decreasing. 10, 5, 3, 2, 0, -1, -2, -3, -2, -1. Poi is where the tangent lines change from decreasing to -2, -1, -0.5, -1/4, 0, 1, 2, 3, to where your tangent lines are increasing. Concave down when the first derivative is decreasing, concave up when the first derivative is increasing. Where the first derivative changes from increasing to decreasing. Remember, the derivative of sine is what? Cosine, right? Where the first derivative is decreasing, the original is concave down. Where the derivative is increasing, the original is concave up. Where the first derivative changes from decreasing to increasing, or vice versa, the original would have a poi. The problem with the first derivative test for concavity is I can't take y prime and solve for increasing and decreasing. I can't do that. But what if you are given the graph of y prime? I can see those are my eyes. I can see where the first derivative is equal to 0 and changes from positive to negative. I can see where the first derivative changes direction. Where the first derivative changes sign, I have extrema. Where the first derivative changes direction, I have poi. So this is extremely useful when I have a graph of the first derivative, or I know what the graph of the first derivative looks like, for instance, cosine. Cool, huh? Sure, forgot I had that up there. Right, of what I was just talking about. First derivative slope values decreasing, first derivative, which are slope values increasing, what that means for the concavity. This is review, right? The second derivative test for concavity, where the second derivative is positive, concave up, soup for you. Where the second derivative is negative, no soup for you. A graph has, if they have a horizontal tangent line and you change concavity, there is a point of inflection. Bam. Okay. That's an awful lot of words. I hope you never write all of those words. But this is the function we started with yesterday. I gave it to you in both standard and factored form. We used the first and second derivative tests to get increasing, decreasing, max, mins, intervals of concave up and down, and points of inflection. We did all of that with derivatives. And this was a bunch of the verbiage. I would not want you to write all of that out. I would want you to be much more succinct, right? And I modeled that for you. Only write if you are asked to justify, explain, or show. If you are just asked to find, you do not need to write anything. No, you do not have to be that wordy. And again, no one is testing to see if your English is proper English. All right, so that's it. And we will do some more practice in class. And we will practice doing the work and doing the writing. And I will see you then.